Okay, we're going to talk about number systems today. Number systems are pretty vital to computer science because computers, at least modern ones, the ones we interact with on a daily basis, tend to work in a binary number system. It's possible to build computers that use other number systems, but electrically, the circuits for binary ones and zeros are a little easier to build, and therefore, most of the computers we use a binary system. We, as people, tend to learn the decimal number system well before we learn alternative number systems. When you learn as a kid to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you're counting in decimal or base 10. So each number system has a base, and what the base tells you is how big the number is that you can count to before you need to go on to a new column or a new digit. So let's take, for example, counting to 10. So I'm allowed to write down a 1, and then I'm allowed to write down a 2, and a 3, and a 4, and a 5, and a 6, and a 7, and an 8, and a 9. But in decimal, in the ones we learn as a kid, I can't put there's not a new symbol for a 10. In fact, the new symbol for 10 borrows two of the symbols that we have from our original set. So if I want to go to the next one, when I've gotten to 9, the next symbol I'm allowed to use is 0. So I put a 0 over again, but that doesn't represent that I've now gone up one more level. So what I do is I take the next available and I put it in this column. And there's my 10. And you'll notice that there's a column of numbers in the ones place and a column of number in the tens place. These are telling us that once I've counted from 0 to 9, I start over again counting from 0 to 9, but I now need a placeholder to represent that I've already done that one time. And if I were to keep counting, here's my placeholder telling me I've already done that once. So here's my 10. And then I would go 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I've done that twice. So I need to put my placeholder in here. So I get to, so these would all have placeholders ones in front of them. And so this is the concept between a base counting system. I'm allowed to do the number of times in the base. So if it's base 10, I'm allowed to go 10 steps before I have to add a new increment to the next column, telling me how many times I've done that. And of course, once we get up to 99, I've now used both of those columns as many times as they can possibly use. So the next column would be 100. I have now done this column 10 times. Okay, so what we think of then is in a number base, we think of each of those sections as a placeholder for a power of the base. So this is 10 to the zeros, this is 10 to the ones, and this is 10 squareds. Or this column, this first column here is representing the digits in the ones place because 10 to the 0th power is a 1. So I can have multiples of 1. So I can have 8 ones, which would be 8. I can have 9 ones, which would be 9. This column is 10 to the first power, or 10. So this is the tens place. And so I can have multiples of that. So if I had, for example, the number here, 29, there would be 9 ones and there would be 2 20s. So this would be the same as, equivalent as 2 times 10 plus 9 times 1, or what we're all familiar with, 29. You can, of course, then 10 squared would be the hundreds place, which you should all be familiar with from your elementary education here. And so we could have 3 of those. So the number 329 represents 3 sets of hundreds, 2 sets of tens, and 9 sets of ones. So this makes sense in our understanding of how we count in decimal. Now, if we were to go to a different system like binary, Binary is another word for base 2 number system. In a base 2 number system, we are allowed to count up with using two symbols. So our first symbol can be 1, and our second symbol can be, or sorry, our first symbol can be 0, and our second symbol can be 1. Once we get to 1, we have to go back and start using 0 over again, which means that we need a placeholder column, the next one over, which could also be zeros and ones. So if I started counting, I would say 0, 1. Now I'm there, so I have to use 0 over again, but I need a placeholder. So this is my very first thing I've put in, second thing I've put in, um, or I should say this is my 0th point I've put in. This is my first item, and this is my second item. So this number here is representing the number 2. It's the second thing. And then if I kept counting, I'm allowed to turn this digit into a 1, and therefore I can have this number, 1, 1, which would be my third item. So that's representing a numeric 3. And now this has to turn back to 0 again, and which means that I have to increment this second column by 1. So one digit higher than a 1 is a 0, and whenever I increment to a 0, I have to add a placeholder in the next column. So this would be the fourth item, or representing digit number 4. Again, back to how number systems work. In base 2, each column represents a power of 2. It's always 2 to the 0th, and then 2 to the first, 2 to the second, 2 to the third, just like we did in any number. Actually, this is how we do it in any number system. It's always the 0th power, the first power, the second power, the third power of the base. So 2 to the 0th power is just, sorry, a 1. Let's see if I can erase here. Is just 1. 2 to the first power is 2. 2 squared is 4. And 2 to the third power is 8. So that means that if I wanted to represent a number like 0, 1, 1, I would take, again, same way, I'd take 1 of the 4s. So this would be 1 times 4 plus 1 times 2 plus 0 times 1 would equal 4 plus 2 plus 0, which equals 6. So this number, 110, is equivalent to our decimal number 6. So this is binary, and this is decimal 6. They represent the exact same number, they just represent them using different symbols in different base. So what are the common bases that we work with? Well, we work with base 2, which we call binary. This is the most fundamental one in a digital computer because voltage levels inside of most modern computer circuitry are based on a low level 0 and a high level 1. So internal to the computers, most things are using a binary number system, binary representation. We also use base 10 in computing. This is known as decimal. And we use that because humans learn that in school, and therefore when we want computers and humans to work well together, we tend to give the humans a chance to work in the number system that they're familiar with. Another one that we use a lot is base 16. Base 16 is called hexadecimal and is utilized to represent a lot of this binary information, but in sort of a shorthand way. You can represent very large numbers with very much fewer symbols. So in like IP version 6 addresses, they're now switching to hexadecimal representations. Usually we use the hex to represent when we want to put a very compact version of a number on the screen, like RGB color codes, for example. And then occasionally we will see base 8, which is known as octal. Whoops, can't spell here. Octal. You don't see this too much anymore. This was common in early computers when memory locations and memory sizes were much smaller. And so usually it's the big three are binary, decimal, and hexadecimal.